So yesterday you guys colored your periodic table. If you missed that somehow when you were coloring your fancy one or you didn't quite finish your coloring, you can always pause this video right now so you can see what you're supposed to color. You don't have to use the same 3 colors I did. But you want to have 3 different colors indicating the nonmetals, the metals, and the metalloids. I encouraged folks yesterday to start by coloring your nonmetals, which don't forget includes hydrogen in that top left-hand corner. And then color those 7 metalloids. Most of them are sitting on top of the staircase that you guys have on your periodic table. And everybody else is a metal. And I do have colored pencils that you guys can grab towards the end of the period if you would really like to. For those of you guys in person, there are a few kind of around if you want them. But yeah, so we're going to go ahead and move on from here. Today you'll be getting a blank periodic table that we're going to label a bunch. Those blank periodic tables are attached below this video here. So you'll want to make sure that you print that off if you're at home. Here's my dumb joke for the day. The element of surprise. You guys, it's pretty good, right? Woo! All right, good talk, everybody. Let's go ahead and talk a little more history here. So Unit 5 does not have as much history as Unit 4 by any means. But there is a little bit of history. And it's just a friendly reminder, I kind of mentioned this yesterday, but Unit 5 is, I think it's like the shortest unit we have all year. So I want to say like 8 or 9 school days from now, so that's a lot less than how many real life days it'll be, your weekends and Thanksgiving break and all that, but it's only like 8 or 9 school days from now that you'll be taking your Unit 5 test. And it's not meant to be intimidating, it's just kind of tell you like, hey, it's just a pretty short unit, like there's not as much stuff on that test as there has been on previous tests. So I just wanted to let you know that we're going to take that Unit 5 test in a couple of weeks' time in school days. And then we will be taking the semester exam shortly after that, after we review for a couple of days. So let's go ahead and talk a little history here. So periodic is not some dead guy's last name. There was no Jimmy Periodic, okay? It is a descriptive title, and it means a regular repeating pattern. A regular repeating pattern. And our first guy is Dimitri Mendeleev. That's not pronounced Mendeleev. I know there are 2 E's towards the end of that name, but it's pronounced Leev, not Leave, Leev. He is credited for coming up with the first periodic table. And he kind of looks like Sirius Black from Harry Potter. He's got the standard really dark hair and the hardcore comb over. He arranged elements based on their properties and increasing atomic mass. And he's just a legend in Russia. The Russians love him, okay? So if you were a high school girl in the 1800s in Russia, okay, you'd have been staring up at your ceiling and you would have had a giant poster of Mendeleev. You're like, oh, Mendeleev, he's amazing. Oh my gosh, I read his blog the other day. Incredible. He's so sensitive and kind. Okay, I don't really know if he was sensitive or kind or whatever, but I'm just saying, I actually had a Russian student my very first year of teaching, and she's like, oh yeah, in Russia, we don't call it the periodic table of elements, we call it Mendeleev's table. They love him. They love him so much. Anyways, he was really sharp. He did leave blank spaces for undiscovered elements, and even predicted some of their properties, which is really crazy. So on his table, he's like, all right, there's going to be an element here and here, and here's what they're going to look like. And he was like, right with a lot of his predictions. You're like, wow, that's really impressive. That is really impressive. So here is his original periodic table. Here are like his notes, okay? So he has like hydrogen in that top left, and we see a lot of familiar names. Like we got, magnesium, aluminum, silicon, phosphorus, all that stuff. And they're arranged by property, so he kind of had different columns based on properties. And they're all in order of atomic mass. And what's kind of crazy is he even left blank spaces. So if you look right here, you gotta erase carefully, you kind of see zinc, okay? And then there's a couple blank spots in between zinc and arsenic. And if you look at your periodic table, zinc is element number 30 and arsenic is number 33. There are a couple of elements that we now know as gallium and germanium in between zinc and arsenic. Mendeleev predicted that germanium and gallium's atomic masses would be about 68 and 70. And they are about 70 and 73. So that's really impressive that he was that close on their masses without having discovered them himself. Okay. He also predicted that right after calcium, but before titanium, there would be another element with a mass of about 45. And he was right on about that. We now know that as scandium. It's very impressive. So we're talking about that guy right there. Right there. How did he do this? Well, if you think about a puzzle piece, so I don't know if you guys have this evil, horrible, terrible family member, but in my family, we like to do puzzles over Thanksgiving break. And I had this evil family member who early on, they like to try and take a piece out of the puzzle box and put it in their pocket. And then towards the end, we're like, where's this last piece? Oh my gosh, we're like losing our minds. And then he'll like put it in there. And he's like, I just want to be the one who put in the last piece. Like, you didn't even help with the puzzle the whole time, you turd. Are you kidding me? That's the most satisfying part, is putting that last piece of the puzzle, and it's evil. It's evil. Anyways, now, when we are looking for that last puzzle piece, inevitably every year that we can't find, even though we've never seen it, we do have a pretty good idea what it looks like. So if you're looking at this piece right here, like, okay, so it's going to have like a nub right here at the top, and down here, there's probably going to be some red on the piece kind of in this area and this area. And like you can kind of, we have a general idea of the shape, some of its properties. We don't know exactly what it'll look like. What's going to be on the piece like right here in the middle, like we don't know. Like we don't really know, but we do kind of know about the edges. And so that's what Mendeleev was doing, where it's like, okay, I don't know exactly what these elements are going to be like, but I can tell you what some of their properties probably are. If that makes sense. So that's what he was kind of doing. Now, we did have to change his way of doing things just a little bit. So if you take a look, if you arrange the periodic table by atomic mass today, it will work almost all the time. So if I start with element number 11, I work my way across. I'm going to read off their masses, starting with sodium. 23, 24, 27, 28, 31, 32, 35, 40. So they're all in order, right? But then if you go to potassium over here, its mass is actually 39. It's a little bit less than argon's. So potassium and argon are not in order of atomic mass. Mendeleev's system would have suggested that you would have potassium come before argon. But then again, you have all these masses in a row right after that. But then you have another exception. So if you look at element number 50, we have tin, about 119, antimony, about 122, tellurium, about 128, and iodine actually goes back down to 127. So iodine's average mass is a little bit lower than tellurium, even though it comes after tellurium on our table. So Mendeleev's table was pretty good. It was pretty good. It wasn't perfect. So we now arrange the table by atomic number, aka the number of protons. aka the number of protons. So element 1 is the one with 1 proton, and 2 is the one with 2 protons, so on and so forth. And it's close to the same order that Mendeleev have. It's a little bit different at points, like your argon and potassiums. But Mendeleev had a pretty solid system, Mr. P, why do we arrange it by atomic number? Like, why is that better? Great question. We'll talk about that more. Now, what you're going to notice is that our periodic table is riddled with patterns, okay? All over the place. And we're going to talk a lot about them in this unit. That's most of this unit, to be honest. But, so like, properties of elements change, and then they repeat with increasing atomic number. So as you go from left to right, elements, 11, 12, 13, 14, 15, 16, the properties tend to change, but then they will sort of repeat every now and then. And we would say that in a periodic way. So periodically, that means every now and then. So when we say there is a pattern that repeats periodically, we'd say this pattern every now and then, you'll see it repeat. So for example, if I were to work through my periodic table, okay, I would see some changes as I go across, but then eventually they'll repeat themselves. Mr. P, what do you mean? Well, if I go ahead and take a look at, let's start in that second row. So I'll come back to the slide here in a second. So let's take a look at lithium over here. Lithium, shiny explosive metal. Beryllium, kind of hard, shiny metal. And we got boron, carbon, less metal-like as you go on. And then we got a gas, really reactive nonmetal, fluorine, incredibly unreactive, non-reactive, neon. And then all of a sudden we have a shiny explosive metal again. And then we have a kind of hard, shiny metal, and then we kind of work our way over, and then we have a really reactive non-metal, and then we have a completely unreactive non-metal. And then all of a sudden we have a shiny explosive metal again. And we just sort of see every so often we get a shiny explosive metal. Every so often we get a gas that won't react with anything. Every so often we get a non-metal that is crazy reactive. And so we'll sort of see this pattern repeat periodically, hence the name periodic table. So let's talk about what these different rows and columns mean. So a column going up and down, vertical column, is a group. Elements that are in the same group have really similar properties. You can kind of think of them as siblings. For example, I had Zach's older brother a few years ago. They did not look exactly the same, but I wasn't shocked when I learned that his last name was what it was. I'm like, okay, yeah, that makes sense. I can tell. There's a resemblance there. So some siblings really look like each other. Other siblings kind of look like each other. Like Izzy and her sister Faith. I'm kind of like, oh, okay. They don't look exactly the same, but I can tell. I can kind of tell they're related there. In my family, it's kind of freakish. So you guys ever do the face swap thing with one of your siblings? Those of you guys that have that. If I did that with my sister, it's creepy how it doesn't look that different, okay? I basically just have my older sister's face. If you just put like a red wig on me and made me like half a foot shorter, be like, yep, that's it. That's the whole thing right there. That's Mr. P's sister. So some groups are crazy similar. Some of them are just kind of similar. But elements in the same column, generally speaking, will have similar chemical and physical properties. I'll be coming back to the slide here in a moment. I'm just going to have you guys do a little bit of labeling here. So, groups. I always like writing this little guy right here. Groups kind of going up and down. And we will come back to this. This is your blank sheet. We'll be going back and forth between the blank sheet and your notes periodically. See what I did there? All right, anyways. I'll come back to this here in a moment. Now, the groups are numbered with Roman numerals 1 through 8. So 1, 2, 3, 4. You don't have to write that down on this because you're about to write it on your blank table. So here's how we number them. This is your group 1. I put a little A there because there's a couple of numbering systems. So there's the A system and the B system. We're going to use the A. This second column is group 2, and I just use the Roman numeral 2 to indicate that. We are going to skip the gap. This is where group 3 is, so we're skipping the gap. 4, remember IV means 4. V means 5. VI means 6. VII means 7. And VIII, 3 I's, means 8. And so there are 8 main groups on the periodic table. And that's how we will number them, 1 through 8. We like to use our Roman numerals for that. All right. Now, what about the rows of the periodic table? Those horizontal rows are called periods. So sort of like a period of time. Like, okay, over a certain amount of time, something will repeat. And so that's why we call going across a row a period, because they will repeat. As you go from one period to the other, they kind of repeat themselves. They follow that regular repeating pattern. That regular repeating pattern. And I always like writing this little graph. And we're like, oh, groups going down, periods go across. You don't have to write that if you don't want to, but I kind of like to write that sometimes. Anyways, we do label our periods, our horizontal rows. We're just going to label them 1 through 7. So if we come back to this guy here. Oh, that's not what I want to do. Where'd he go? There he is. All right. So down the side here, I go ahead and label these. Uh-oh. That's not what I want. Why does it think that that is a marker? All right. Here we go. 1, 2, 3, 4, 5, 6, 7. So, for example, if I were to say, hey, what element is in group 3, period 2? You'd be like, okay, group 3 is right here. period 2 is that second row, so he's talking about this element right there. Okay? So that's sort of like a coordination system for you. So sort of like longitude, latitude. But anyways, so that's how we kind of use those groups, numbers, period numbers, that kind of thing. Alrighty. So now we got to talk about those things we colored yesterday, the metals, the metalloids, and the nonmetals. Alright, so metals. Now what I'm about to say is not true for every single metal that has ever existed, but it's true for most of them most of the time. Okay? Generally speaking, metals are good conductors. They are shiny, they're malleable, and they're ductile. Or ductile, never remember. So, for example, a paper clip is a good example. Paper clips are good conductors. They are shiny. Malleable means you can bend it without breaking it. So here, I can bend this, and it won't break on me. Okay? I can bend it, not breaking, not breaking. And I can also easily shape it. I can kind of make this whatever shape I want. So if I want to kind of bend this into a triangle, let's say, I can do that. I've kind of bent it a lot today, so it's a little unhappy with me. But you guys get the idea. Okay? So with metals, you can kind of do that. Metals also just love to give away their electrons, which means, generally speaking, they are going to have positive charges. Generally speaking, they're going to have positive charges. You will notice on every single atomic structure chart you guys did in Unit 4, whenever you had a metal, it was never negative. Not once. Just to kind of set you guys up for Unit 5. So, like if you had aluminum on a problem, for example, if it was charged, it was going to be like a +3. It was never going to be negative something. Yes, sir?
There is a difference between malleable and ductile, right?
Yeah, ductile means you can kind of shape it easily. So you can kind of form it into any shape you want. So you can make it like really thin, or you can make it really thick. You can kind of make it in whatever shape you want. Malleable just means you can bend it, and it won't snap on you. Okay? What's that?
I think you explained that already, but thank you for doing it.
Yeah, no problem. No problem. Clarifying questions. Now, you don't have to necessarily draw this if you don't want to, but I kind of draw this little umbrella. So notice how I'm going underneath the hydrogen there. And generally speaking, this is on your blank periodic table, so it's not your fancy one. You don't have to be sad about goofing it up. But underneath that umbrella, you're going to have those metals. Okay? They generally give away their electrons, which means they will be positive. Okay, so folks underneath that umbrella, for the most part, will tend to be positive because they're giving away electrons. And I'll come right back to this umbrella if you don't quite draw that yet. Now, nonmetals, they have a lot of the opposite. Now, again, this isn't true for every single nonmetal, but this is true for most of them. Nonmetals, generally speaking, are poor conductors. They are dull. They're not very shiny. And they are brittle. You can't really shape them very well. So, for example, I have a nonmetal here in my hands. I wonder if I can bend this without breaking it. Apparently not. Okay? They're very brittle. They don't like it when you try and bend them. They just snap in half. And nonmetals, they kind of love to take electrons, which means they will typically have a negative charge. Again, on your atomic structure worksheets in Unit 4, you never had one where a nonmetal was positive. Never happened. Didn't happen. Okay? So your chlorine on one of those problems was -1, and that was on purpose. Chlorine would never be +1. That's just not going to happen. And so, if you're going back to the umbrella, folks above that umbrella, which would include hydrogen on the far left-hand, top left-hand corner, they generally are, those are nonmetals, and they generally take electrons. So the metal's like, anyone want an electron? And nonmetal's like, yes, sir, full send. Send it my way, please. And so nonmetals tend to be negative. Metals tend to be positive. And they have very different properties. Before you even walked into this room today, you probably could have visually told me whether something was a metal or a non-metal lots of times. Like, oh, it's kind of shiny. Okay, I guess it's a metal. Generally speaking, from what I know about metals, they're kind of shiny. Not all of them, but, you know, most of them. Now, let's talk about the metalloids. So those are the folks that are hanging out around the staircase. Remember, your staircase on your fancy table is right around here. So the folks close to that staircase are called metalloids. And this is not that shocking, but they have properties of both metals and nonmetals. People dedicate their whole careers to a single metalloid in its study because they are very versatile and they can do quite a lot. So, for example, silicon. That is used in certain kinds of plastic surgery to make some things bigger, if you will. But it is also used all the time in computers, like hardware and that kind of thing. So it's really versatile. It's like super versatile. So there's a lot of money to be made with silicon because it can do a lot of different things and it's pretty unique in that way. And so there are 7 different metalloids here. And so we're back over here. Your metalloids, again, this is why this is a blanked out periodic table. They're kind of generally right here, so kind of just write them diagonally in that corner. Those are your metalloids. Those are your metalloids. So now we got to talk about different groups on that periodic table. Now there are a lot of groups that you need to remember their names, remember where they are on the periodic table because it will help you have everything organized in your mind. So this is kind of like remembering different streets in your neighborhood. It's very useful for you to remember which one's which, okay? Especially if you ever get lost as a kid. So, group 1A on the far left-hand side. They are extremely reactive metals, and they are called alkali metals. These things will blow up if you put them in water. I will be doing a demonstration of that later this unit, which is fun. We have these in the building, but they are stored in mineral oil, so they can't even interact with the moisture in the air. So we really don't want them anywhere near water. So alkali metals. I'll be going back and forth between this slide and this one right here a million times. So on that far left-hand side, I don't know why that changed on its own. On that far left-hand side, you have your alkali metals right there. Alkali metals. So that first group. So anyone in that first group is an alkali metal. So your potassiums, your sodiums, lithiums, all that good stuff. All of those will blow up in water. Group 2A, right next door, those are called the alkaline, N-E on the end of that. So it's the word alkali again, but with an N-E on the end. Earth metals. And they're reactive. They're not as reactive as the alkali metals. So I'm like, hey, I have a crazy reactive metal. Do you think it's alkali or alkaline earth? You're like, well, it's alkali if it's crazy reactive. So that's where you have your calcium, your magnesium, strontium, all that good stuff. So when I go over here, that's where your alkaline earth metals are. Alkaline earth metals. Now the big block in the middle of the periodic table that separates the metals on the left from the nonmetals on the right, we call those transition metals. So that's where you get a lot of the fancy ones, your coppers, your golds, your silvers, your platinums, zincs, cobalt, nickel. I mean, there's all kinds of ones in there. Manganese, iron, chromium, titanium, all those. So again, that's that big block here in the middle. We call those transition metals. So it's like a 4x10 block. So like this whole thing right here, those are transition metals. The big chunk below the periodic table, those are called your rare earth metals. So a lot of those are man-made. They only last for like a fraction of a second. Not all of them, but a lot of them. Rare earth metals are rarely found on Earth. That name's not supposed to be tricky by any means. Here they are, rare earth metals. Again, you're only labeling this on your blank periodic table, not your fancy one. You wouldn't have room for that. Now, group 7A, that's that second to last column on the right-hand side. Those are extremely reactive nonmetals. So those are your fluorines, your chlorines, your iodines, bromines, all that stuff. We'll get to see this more during this unit, but fluorine is kind of considered the bully on the periodic table, in my mind. It's a real bully. Okay, it's a little rough with other elements, if you will. But we call group 7A the halogens. The halogens. Halogens. So that's these folks right here. These are all halogens. Crazy, crazy reactive. So they're very reactive just like the alkali metals, but they are nonmetals. Okay, so all the halogens are nonmetals. They're still reactive, but they are nonmetals. And lastly, we have the snooty folks in group 8 on the very far right-hand side, the last column. Those are called the noble gases. They are not reactive, so we say the word inert. So inert means non-reactive. They won't play with anybody. Okay? They're the elements where other elements like, hey, you want to form a bond? And they're like, no, we don't need you. Thank you very much. Off you go, potassium. Nobody likes you. Okay? The noble gases do not bond with any other elements. They don't like any other elements. They're snooty, and they will not react with anybody. So the noble gases are on that far right-hand side. Your heliums, your neons, your argons, all that good stuff. Noble gases. Noble gases. Oh, we're noble. We're so noble. So, if I were to ask you, hey, what family is strontium in? What family is strontium in? You would say what? Alkaline earth metals. That's right. Strontium's element number 38. I could also ask you, like, hey, what is the period for halogen? What is the period for halogen? Like, okay, well, period 4 is this fourth row right here. Okay, so it's going to be this halogen. That would be what? Bromine. Yep, that's going to be bromine. And again, I could always go like, hey, what is, the group 7 period 5 element? So, okay, group 7, again, that's just halogens. Period 5, like, all right, there's second, third, fourth, fifth period. So that would be your iodine. That would be your iodine, okay? So there are a lot of different ways I could ask you about places on the periodic table. Now we have one more slide of notes here. One more slide. And this is going to be sort of like a Section 9 4.18 situation. I'm about to say this many times and burn it to your brain. But there are some atoms that will never be found alone in nature. Okay, they're always going to have a bond. We call these diatomic, breaking that apart. So I have di meaning 2, atomic referring to, stop that, atoms. So they're always going to be found as 2 atoms. Oh my goodness, I don't know why. Stop! Oh my gosh, my smartboard is being so evil today. Stop it. I'm not going to try and write that S on atoms. I quit. So they're elements that will always be found as a pairing. So for example, in biology class, you may have noticed that you never saw O by itself. It was always O2. You never saw O by itself. It was always O2. Now, it can be bonded in something else, okay? So like carbon dioxide has oxygen in it, and it has carbon, all that good stuff. But what I'm saying is, it's always going to be bonded. If it's not bonded with another element, it will just bond with itself. So there are 7 elements that will just bond with themselves, and there's nobody else to play with. Okay? Here they are. I do expect you guys to memorize this, if you will. So I have some tricks for you. So we have H2, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. There are a few ways to memorize this. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. So here's one of them. So those are 7 elements right there. If you look at any old periodic table, here are 6 of them right here. And look at what shape they form. They form the number 7. And just remember, hydrogen goes with them. Hydrogen's a hipster element, so if there's ever an exception to the rule, it's often hydrogen. Like, oh yeah, these elements it is, well, except for hydrogen. And then these ones all follow this pattern, well, except for hydrogen. So you can remember, hey, there's 7 of them. They form the number 7 plus hydrogen, if you want. And here's the other way that requires less intelligence, and here's how I remember it. Hofbrinkel. Hofbrinkel. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. Hofbrinkel, Hofbrinkel, Hofbrinkel. Here's where I'm going to say it 1,000 times in a row to get burned into your brain. Hofbrinkel, Hofbrinkel. Oh, man, I stepped in Hofbrinkel today on my way to school. You smell like some real Hofbrinkel. You look me in the Hofbrinkel and say that to my Hofbrinkel. Hey, you guys want some Hofbrinkel? You look like you can get down with some Hofbrinkel. Dude, man, what, you just Hofbrinkel or something? Oh, I'm going to Hofbrinkel. Hofbrinkel, Hofbrinkel, Hofbrinkel. Hofbrinkel, Hofbrinkel. Hey, do you guys want Hofbrinkel? Section 9. Hofbrinkel, Hofbrinkel. Hey, Hudson, can you make sure you turn off the Hofbrinkel when you go to the Hofbrinkel? And if you Hofbrinkel one more Hofbrinkel, I swear to Hofbrinkel, I will Hofbrinkel up, down, and all around. Okay? Hofbrinkel, 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 Hofbrinkel. Okay? Oh, you look very Hofbrinkel today. Oh my gosh. If she isn't a Hofbrinkel, then I don't know what a Hofbrinkel is. Hofbrinkel, 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 Hofbrinkel. Section 9, 4.18, Hofbrinkel, okay? Mr. P, why do I have to memorize that those ones are not alone? It won't be immediately obvious, but there will be times down the road in Unit 5, 6, 7, and 8 where you're about to make a colossal mistake on a very long math problem, and you're like, oh, wait, it's O2, not just O. You know, I really was annoyed at that Hofbrinkel thing, but I'm glad I remember it right now. So there will just be times where this will just bail you out, okay? It may not become immediately obvious, but this will just be a nice thing to have memorized for down the road. Okie dokie. So that's it for our notes here today.